So this is part 2 of chapter 2, and today we're going to discuss why ppm as the x-axis for NMR. So that's parts per million. Because in like UV, vis, let's see, fluorescence, you may use the x-axis in nanometers, and like FTIR, we do something like in wave numbers. And so why parts per million is the x-axis. So for like a proton NMR, it runs from 0 parts per million out to about 12, with 0 parts per million being defined by the chemical shift of TMS. So that's tetramethylsilane. So that's these protons on the carbons are defined as 0. ppm. And if you're running carbon, the carbons here are defined as 0 also, for C13. And the reason is if you go into the in an NMR room, and you may see like a 400 megahertz NMR or a 500 megahertz NMR. Those are common in organic type chemistry situations. But these are the what I call the nominal frequency. It's not really the true frequency. It's just basically the approximate frequency. Because every magnet in every lab is going to have a different magnetic field strength, and the frequency that protons absorb, so the frequency that you observe is proportional to the magnetic field. But even among 500 megahertz magnets, lab 1, lab 2, and lab 3, they'll all have a 500 megahertz magnet, but one may be 500.01, 500.2, 499.9, and dot 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 dot. So they're all different, and so they're just basically saying it's approximately 500 megahertz. So you know, that lab may have something like 400.012 and or 3. Let's put a 3 here. Let's make it 1, 2. Get rid of that guy. And this lab may have something like 500.0172 as the actual true frequency that protons resonate at. And so, like I said, the frequency of your particular resonance, let's say, let's put something right here at let's take this one, let's put something at 2, let's say 2.09. 2.09. Let's see at a peak there. And on this spectrometer, it's going to be in the 500 megahertz range. And on this spectrometer, that peak is going to be somewhere in the 400 megahertz range. And so if every lab is, say, reporting different frequencies, even among these different labs that have roughly the same magnetic field, they're all going to have a slightly different frequency. So the ppm scale is basically to get everybody on the same footing. So no matter whether you run the compound on a 400 or a 500, you're always going to get 2.09 as the frequency. And so on a 400 megahertz, that peak may have 400.012836 megahertz as its frequency. And on a 500 megahertz, it may be 500.018245 megahertz as its frequency. They're both the same peak at 202.09 ppm, but on that magnet, this is the frequency, and this is the frequency. So it would be kind of nonsensical to report this in the literature that I got a peak at 500.01824, and this guy that has the 400 megahertz magnet, he has no idea what you're talking about. It appears at 400. But if you just say that your parts per million is equal to your peak minus the spectrometer frequency divided by the spectrometer frequency times a million. And so if we put in, 400.012836 minus the spectrometer of 400.012 divided by 400.012, you're going to get 2.09. And likewise, if you did that with the 500 megahertz spectrometer, where you put in 500.018245 minus the spectrometer's frequency, 0172 divided by 500.0172 times a million. Oops, I forgot that up there. Times a million. You're going to get 2.09. So even though they had different frequencies, once you do this, basically this parts per million normalization formula, then everybody's reporting the exact same chemical shift and parts per million. And so that's why we use the chemical shift. So because everybody has a different magnet with a different magnetic field in their lab, but everybody wants to report the exact same parts per million number. So this 2.09 is the amount of, say, chemical shift that is from the reference point. So the reference point was 0 ppm, and we add the 2.09, and then we end up with 2.09 as the chemical shift of that peak.